Hi guys, good evening everyone. Welcome to the session and welcome to the India's most comprehensive preparation platform, that is the Byjus Exam Prep, and welcome once again to the GATE Formula series. Yes, the GATE Formula 1 series, and now this time I'm live with the next and yet another important subject, that is the electromagnetic theory. Yes, so in this session, the intent is to get all your formulas related to electromagnetic theory for the branch of electrical, electronics and instrumentation. Yes guys, so the topic that we are going to cover today, in this session of EMFT is the one which is common to all EC, EE and IN. So electrostats, magnetostats, time varying fields and all those things up to the Maxwell's equation part. Right, up to the Maxwell's equation part, that is what we are going to cover. Right, then in another session entirely up to the Maxwell's equation we are going to cover, and then in another session we will take up the rest of the topics of electromagnetic theory. Very good evening all. Quickly keep joining and update your friends that the session is live. Right, so in another session that is going to be on Monday, we will cover up the topics which are exclusively for EC. Yes, we all know there are some topics which are exclusively for EC, right? That we are going to cover up on the Monday. Okay, that is transmission line, wave propagation, reflection, refraction, antennas, waveguides, all the stuff we are going to cover on the next session. Right, so very good evening, and this is going to give you an entire formula book for the electromagnetic theory in one shot, up to the topics which are common for EC, EE and IN, as I repeat. Right, so all formula in one shot in one particular session. Let us get started. And in case somebody new to my session, this is a brief intro about me. This is your mentor and educator Rakesh, and I have secured All India rank 9th in the GATE examination, completed my masters from Indian Institute of Science, Bangalore. I have more than 12 years of experience, trained more than 50,000 students in my journey, and commonly I deal with the subjects mentioned here. Right, these are my major area of expertise. Okay, right guys, you can also connect me through my Telegram group. Okay, through my Telegram group, where you will get, I'll share you the link of the Telegram group separately, but in that Telegram you can get even the PDF of today's session and all other sessions. All my session notifications and all important updates will be there in that particular Telegram. One more quick update before we start off the session, that guys, on the coming Sunday, that is just 2 days later, at 9 p.m. Sunday night 9 p.m. I am bringing you a session. Okay, I'll just hide myself for a moment. I am bringing you a session where we are going to talk about, okay, what are 3 crucial mistakes that GATE aspirants usually does in the last moment, and because of that they are hampering their rank, they are hampering their chances of good performance in the GATE examination. So what are those 3 mistakes that you should clearly avoid in the last 3 months of the preparation? Yes, November, December, January, nearly 3 months are left. Okay, right, nearly 3 months are left. Okay, chalo. Okay, so guys, let us get started. Very good evening all. Very good evening. No, I'm full-time as teacher. I'm into teaching industry, Rajkumar, since 12 years. Right. All right guys, quickly come on. So all those who are live, quickly share the session, like the session. Let us start with the positive motivation. Let us start with the positive intent, and let's get moving on with the session. Okay, the number one concept, of course, that we are beginning up, and that is important to begin up in the EMFT, is the basic Coulomb's law. Okay, the basic law to study in the electrostatics, in the electrostatic fields. Right, the Coulomb's law. Okay, which states that the force between 2 point charges, I will give you the final expression in the vector form also. Let's get started quickly. So force between 2 point charges Q1 and Q2 is number 1 along the line joining them. Okay, we'll represent this with the help of vector also. It is directly proportional to the product Q1 Q2. Actually, it is proportional to both the charges Q1 and Q2, and it is inversely proportional to the square of the distance. Higher the distance, lesser is the force, and that is given by eventually that is eventually written as force being proportional to Q1, Q2, also proportional to 1 by R square, and removing the constant, removing the proportionality sign, we introduce the constant of proportionality, which is known as the K, and F is given by K Q1, Q2 divided by R square, where K is the constant given by 1 upon 4 pi epsilon, and it is 1 upon 4 pi epsilon naught if you are specifically talking about the free space, where we all know epsilon naught is known as the permittivity of the free space. So K is 1 upon 4 pi epsilon naught is known as the permittivity of the free space. Okay, if it is other than free space, you can use the permittivity of that particular medium. Right, and the value of epsilon naught, guys, for numericals, you should always remember both the values for epsilon naught: 8.854 10 power minus 12 and also 1 upon 36 by 10 power minus 9 farad per meter. So eventually we can write F is equal to Q1 Q2 by 4 pi epsilon naught R square. But we all know that force is a vector quantity. So what is the final representation of Coulomb's law? This is the first area where questions are expected. So final vector form of the Coulomb's law, let us understand with that. Just a second, guys. Let us understand with that. Hi, good evening all, keep joining. Good evening, keep joining. Right, so dekhte hain. Okay, so what is the final vector form? Understand this way: there is a point charge Q1, there is the another point charge Q2, and there is a line joining Q1 and Q2. Okay, there is a line joining Q1 and Q2. Let's say Q1 is at the point A, Q2 is at some point B, and let's say R is the vector joining A to B. What is the vector joining any 2 points? R is the vector A to B, and that is written as vector B minus vector A, position vector of B minus position vector of A. So you are given 2 coordinates where the charges are located, Q1 and Q2. You can clearly find the vector joining the 2 points. You can clearly find out the vector joining the 2 points as OB minus OA. So what is the unit vector R hat? What is the unit vector from Q1 to Q2? So unit vector is always calculated as a vector divided by its magnitude. Simply I write down the magnitude as R. Okay, let's say R is the magnitude of the vector. That is the length of the line AB. Okay, that is the length of the line AB. So firstly, you should find the vector R, and then in the final vector form, force is given by K Q1 Q2 divided by R square, where R is the distance. Direction is R hat. Direction is the vector joining the points Q1 and Q2. Direction is the vector from point A to point B. Right, Ashish, your sound is there. Everybody, good evening. Audio, video, everything should be clear. Right. Now, this force is given by K, Q1, Q2. If you write down in terms of vector R, so vector R is vector R divided by the R hat. Vector R is divided by the R hat. Sorry. Correct. Vector R divided by its magnitude. So if I replace, the denominator is actually going to become the R cube. The denominator is actually going to become the R cube. So this is what is the final representation of, the Coulomb's law, correct? The final representation of Coulomb's law in the vector form. Okay. Now the concept of electric field, as we all know, guys, we are not going into derivation or detailed theory. We are going into the formula 1, as the series says, formula 1, F1, formulas in quick one shot of the session. So let us come to the concept of electric field also, which is defined as the force experienced by a unit charge when it is placed in the electric field of some other source, right? Force per unit charge. So if we take it first of all due to point charge, then I will give you the formula due to continuous charge distributions also. So due to the point charge, let us once again, look into this way. Let us write down the final form of the electric field. Suppose this is a point charge Q, and which is located at some point A, in the space. This is some point P, the point where the electric field has to be measured. I will call it as point of observation. Okay, I will call it as the point of observation. Okay, what is the electric field at the point A? Let us say this is what is my intent. What is the electric field at the point P? What is the electric field at the point P, at the point of observation that is to be measured. So guys, as I'm telling you, electric field is given by KQ upon R square. It is as simple as that. Suppose there was a charge here, that is QT. Suppose there was a charge here QT. Then what is the force? If you write down in terms of force, it becomes KQQT divided by R square according to Coulomb's law. But what is the force experienced per unit test charge? Okay, so when you divide by QT, okay, this is the formula for force in that case. But when you divide by QT, F upon QT, you will get the formula KQ by R square, and that is what is known as the electric field. That is what is known as the electric field due to the point charge. So let us write down in terms of electric field. Okay, so it is KQ by R square. Direction, it is along the line joining point A to the point P. Okay, so what is the vector R here? The vector R here is the vector from point A where the charge is placed up to the point of observation. So what is the vector R hat? Unit vector. Unit vector is the vector R divided by its own magnitude. So vector R by R. So if you write down in terms of vector R, this becomes KQ upon RQ vector R. Right, these are what is the, this is the form of the electric field due to point charge. This is also important. You can be expecting some questions from here. The electric field due to the point charge. Okay, then next the question and the formula that you can expect is from the flux. Before going to the flux, let me tell you one or two important points about the electric field lines. So as you're able to see, let me come to the previous picture. This is the source. If this is the source charge, where can you expect the, where can you experience the electric field? Okay, where can be the point P? So even if the point P is here, okay, you can calculate the electric field at the point P. Point P may be located here. This also will have some electric field. If this is the point of observation, there will be also some electric field at the point P. The idea is that test charge I was telling you, now you can place the test charge anywhere around the source charge. You can place the test charge anywhere around the source charge, and that is going to experience the electric field. So where is the electric field around the source? It is in all directions about this point charge. All directions about point charge, it will be a spherical distribution actually, right? You can construct a sphere about this point charge and the electric field will be experienced everywhere within that spherical region. So electric field is in a direction, which is radially away from the source. Okay, it is here also, here also, here also, here also, here also, everywhere around the source, and we represent this electric field by the concept of electric field lines, which are hypothetical lines, right? We represent it by the idea of electric field lines. This is what is mentioned here, electric field lines, which are hypothetical lines. There are no physical lines. We are just drawing to represent what electric field could be. Let me just hide myself for a moment. Let me explain you this. So this is what is the source charge Q. This is the source charge Q, right, where whose electric field is measured, and I am telling you electric field can be at any of these places. It is radially away from the source. Acha ji. Number two, now very clearly you can measure, guys. Suppose, okay, what is the spacing between the field lines here and what is the spacing between the field lines here? So let's say this is some point A, let's say this is some point B. Okay, let's say this is some distance D1, this is some distance D2. We all know that which electric field has to be more? We all know that which electric field has to be more? Electric field at A will be greater than the electric field at B. Okay, because the electric field is inversely proportional to the distance. So if the distance is more, electric field will be less. Okay, so electric field at A will be more than the electric field at B. But what is the relation between D1 and D2? You are able to see? The D1, the length of the arc D1 is less than the length of the arc D2, as you are able to clearly see in the picture. Okay, and I can say that the spacing of the field lines is inversely proportional to the strength of the field. So now what does this show? Very clearly you can understand what does this show. It is simply a representation that in a place at a point where electric field lines are more closer to each other, more compact, more closer to each other, there the field strength is more. Electric field then always flows from higher to lower potential due to the relation that I am going to consider with potential. Electric field is minus of the gradient of V. Okay, electric field does not exist inside a perfect conductor, and electric field lines never form a closed loop. For dipole they appear as closed loop, but for magnetic field lines, for any type of source, the magnetic field lines always forms a closed loop. Okay, now the concept of flux, which was first of all demonstrated by the Faraday's experiment. What was the Faraday's experiment? He took two concentric spheres. He took two concentric spheres, the inner sphere, and they were, the inner sphere and inner sphere was inside the outer sphere, and they were separated by any dielectric material. Okay. The inner sphere was given some charge plus Q, and the outer sphere was initially discharged by connecting to the ground. The outer sphere was initially discharged by connecting it to the ground, and the inner sphere was given some known charge plus Q. Okay. What Faraday observed? After certain time, Faraday observed that the inner body of the outer sphere, this also developed the charge. Also, initially it was discharged. Initially this was discharged by connecting to the ground, but this also developed a charge that was opposite in sign but equal in magnitude to the charge placed at the inner sphere. This led to the concept of the movement of charge, the displacement of charge. In a way, Faraday concluded that there is some sort of movement. See, there was no charge on the outer sphere, but there was only the charge from the inner sphere, and he referred to this as the phenomena that there is some movement, there is some displacement of the charge from the inner body to the outer body, and this displacement of the charge was named as displacement flux, or it was simply named as electric flux, Xi. And how much of the flux moved? What was the displacement? It was the displacement of the charge Q, and the flux being measured was equal to Q. The flux being measured was simply equal to the Q. Okay. There came the concept of electric flux. And even if you talk about flux actually represents, even the literature meaning of flux, if you see, it represents movement of something. So here it is the flux of electric charge. We call it as the electric flux, the movement of charge from the inner sphere to the outer sphere. And this only was, properly mathematically modulated by Gauss. Okay, the experiment, the observation was initially given by Faraday, later on properly formulated by Gauss, and here we get the Gauss law as well, right? Oh, Rajkumar, okay. You're asking a very basic doubt. Please connect to me on the Telegram once, because otherwise, if I go out of the topic, the session and the content will be disturbed. Okay, Rajkumar. So please float your doubt to me in the Telegram separately so that we can have a discussion. You can send a DM to me in the Telegram. Okay. Then how much is the density of flux at the inner sphere? How much is the density of the flux at inner sphere? Now, density of the flux will be represented here as flux per unit surface area. How much is the flux? Q, right? How much is the flux? Q. Isko hide karte hain yahan pe, right? So it is, how much is the flux? You can represent Xi, but Xi is equal to Q, and divided by the surface area. What is the surface area of the sphere? It is 4 pi a square, or you can also call it as Q divided by 4 pi r square. Yeah, what is the density of flux? Okay, what is the density of the flux at the outer sphere? What is the density of the flux? This is with respect to the inner sphere. What is the density of flux at the outer sphere? So how much how much charge appeared on the outer sphere? That is also equal to Q, right? That is also equal to Q, and then divided by 4 pi b square. The outer radius is given to you as b, right? Good evening all. This flux per unit surface area is the flux density represented by D. And what is the relation between D and E? Let's finally go to the formula. Formulas are important for us. This is the formula session. The final relation between D and E, you can go through it later on as well. The D is given by the epsilon E. The electric flux density is given by epsilon E, where epsilon is the permittivity of the medium, which can be represented as epsilon naught, epsilon r. We all know that epsilon r is the relative permittivity of the medium, that is the permittivity divided by the permittivity of the free space. Okay. Now, once you know the electric flux density, you can calculate the total flux. What is the total flux? Very good evening. What is the total flux? Since the D is the flux density, flux per unit surface area, the total flux can be obtained by the surface integral of the flux density vector. The surface integral of the flux density vector. And as I told you, with the help of Faraday's experiment, Gauss mathematically modulated this and came to the conclusion known as the Gauss law, which states that the total electric flux through any closed surface total electric flux through any closed surface is equal to the charge enclosed by that surface. The total electric flux through any closed surface is equal to the charge enclosed by that surface, and Xi is equal to the Q enclosed. Xi is equal to the Q enclosed. Xi is equal to the Q enclosed. Right. Xi is equal to the Q enclosed. Right, everyone? Okay, for example, if you want to understand this, let us take an example. Suppose there are some point charges. Let's understand with the help of point charges, and there is any closed surface. It could be any closed surface, be it spherical or any type of closed surface, and there are the charges, suppose Q1, Q2, Q3, there is another charge here, Q4, and etc, etc, etc. What is, guys, the total flux crossing this closed surface? Gauss law is applicable for closed surface, and the total flux crossing any closed surface is equal to the charge enclosed by it, and the charge enclosed is Q1 plus Q2 plus Q3. But is it including Q4? No, that should not be included because that is not inside the closed surface. The flux crossing any closed surface is equal to charge enclosed by it. Please remember, it is equal to the charge enclosed by. Directly you can expect the questions on this formula as well related to Gauss law. And then the Gauss law, Xi is equal to Q enclosed, was generalized in terms of the Maxwell's equation. So see, Xi is equal to Q enclosed. The flux, as I told you, can be calculated as integral d dot ds, but we are applying Gauss law, which is applicable only for closed surface. So integral d dot ds over a closed surface is equal to charge enclosed. What is the charge enclosed? You can calculate the charge enclosed by integral rho v dv, where rho v is known as the volume charge density of the medium. Rho v can be known as the volume charge density of the medium, right? So the total charge enclosed in a medium is equal to the volume integral of the volume charge density. Charge per unit volume, if you know, you can calculate the total charge within that volume. But now you can apply the Gauss divergence theorem on the left hand side, because surface integral over a closed surface can be simplified using the Gauss divergence theorem. And once you apply the Gauss divergence theorem, you get del dot d dv. The surface integral of a vector along a closed surface is equal to the volume integral of the divergence of the vector is equal to the volume integral of the divergence of the vector. So this is equal to integral del dot d dv. It is equal to rho v dv, and both the sides are now volume integral. You can compare the integrands and you can get the answer. Del dot d is equal to rho v. Very, very important, the Maxwell's equation. So 4 Maxwell's equation I will summarize for you today, right? And this is the first of them. This is the first of them, dependent on the Gauss law. Dependent on the Gauss law. Del dot d equal to rho v. So this is one area where, very important area, whether it is, EC branch, W or IN, where you expect the question. Okay, given the D, given the flux density, calculate the volume charge density rho v. Yeah, sometimes they give you the E. Okay, given E, find the rho v. So rho v is what? Del dot d. That is equal to del dot epsilon E. The electric field may be given, you can calculate del dot epsilon E, right? Or that is equal to epsilon del dot E. That is also one probable question, right? So this is one area where you can, be ready to expect the question. Gauss law, the charge enclosed or the volume charge density, all that thing remains to be very important. Hope it is all clear up to this point. There's a quick formula revision of all, and then let's move towards the next one as well. Just a second. Sure. Right, let's move ahead to the next concept. Okay, what is the electric field due to the continuous charge distributions like line charge, surface charge and the volume charge? Okay, we have seen of the point charge. Let us move towards the different charge distributions now. Okay, what about the infinite line charge? Infinite line charge, see, again, there is nothing like infinity, but infinite is used to here represent the long line charge, right? A line charge of very long length, large length. Long length. The length is much greater than the diameter of the wire. It's like a thin wire. Okay. Thank you, Sri Lakshmi. Okay. So let rho L be the uniform charge density. This density is missing here. Okay, consider a line charge having the charge density rho L. That is, what is the charge available on the wire, available on the line per unit meter. If I take only 1 meter, okay, suppose the charge here in this 1 meter section is Q, and that is known as rho L. The charge in 1 meter of the wire. Okay. After applying, these are all applied by the Gauss law, these are all taken by Gauss law. After applying the Gauss law, what is the electric field we obtain? The electric field is actually given by rho L upon 2 pi epsilon naught rho A rho. What is rho L? It is the line charge density, charge per unit length, upon 2 pi epsilon naught. Epsilon naught is the permittivity of free space. If it is not free space, you can use the epsilon of that particular medium. Okay, A rho. What is A rho? Okay, A rho, it is the rho direction of the cylindrical coordinate system. This is A rho actually. Okay, the rho of the cylindrical coordinate system. How do you represent this rho? If I go to the picture, so what is the rho of the cylindrical coordinate system? It is a direction which is radially away from the z-axis. Now, a direction perpendicular away from the z-axis, okay, is known as the rho direction. This is what will be the A rho direction. Let me represent here separately. This is what is the A rho direction. The unit vector perpendicular to the z-axis, okay, anywhere around the z-axis is the A rho direction. The radius of the cylinder. So imagine if it is a cylinder whose axis is the z-axis, how will if there is a cylinder with the axis at the z-axis, how do you increase the radius of the cylinder? Okay, by moving away from the z-axis, you can enlarge and enlarge and enlarge the cylinder, right? So rho L upon 2 pi epsilon naught rho A rho. What is the rho? It is the perpendicular distance. It is the perpendicular distance of the point of observation. You are measuring the field here. Okay, the perpendicular distance from the point of observation from the line charge. That is known as the rho. That is known as the rho. Let me mention here. This is known as the perpendicular distance of the point of observation from the axis of the line. From the axis of the line charge, right? Then the next case that you can expect, so this was this was a long line, okay, carrying a charge distributed uniformly over it, okay, something like this, a line charge. It can be a surface charge as well, an entire surface carrying some charge. Okay, let's say this is the entire surface. Again, we'll talk about a long surface, okay. This again nothing practically infinite, but a very long sheet of wire like this sheet carrying the charge distributed uniformly over it. And first of all, we define the charge density of it. Once again, let me mention that this has to be density. This is missing here. So we have an infinite sheet. Once again, a very long, huge sheet carrying the charge rho S. That is the charge density. That is the charge. If I suppose cut 1 square meter of this sheet. If I suppose cut 1 square meter of the sheet, how much is the charge in 1 square meter? Suppose that is Q, and that is equal to rho S actually. That is equal to rho S, the charge per 1 square meter of the sheet. Okay. This sheet has been assumed in the z equal to 0 plane, z equal to 0 plane bole to xy plane, although it could be in any other plane, not necessarily xy plane. After applying the Gauss law, what is the final next formula important for you? Electric field is given by rho S divided by 2 epsilon naught A rho. Rho S, surface charge density of the sheet, epsilon naught permittivity of free space, an cap. What is this an cap? It is the unit vector. It is the unit vector normal to the sheet. It is the unit vector normal to the sheet towards the point of observation. Unit vector normal to the sheet toward the point of observation, right? This is how it is. Okay, suppose this is the point of observation, so we take a vector perpendicular to the sheet. Now here the sheet is in the xy plane, so what will be the an cap here? Here the sheet is in xy plane, so what is the unit vector normal to the xy plane? It is az. Okay, but in general the sheet may not be in the xy plane, it could be in any plane, so we take a vector normal to that particular sheet. The next important formula for you is with respect to a volume charge, an entire volume, like a spherical ball carrying the charge Q, and we define the volume charge density here as rho V. What is the rho V here? If you just imagine in this formula, what is the rho V? It is simply given by Q, rho V, volume charge density, charge per unit volume, charge, total charge Q divided by unit volume, and the volume of the sphere is given by 4 by 3 pi a cube, where a is the radius of the cylinder. The radius considered here is a, so that the total volume is 4 by 3 pi a cube. Okay. 4 by 3 pi a cube. This is what is the final formula. Again, after applying the Gauss law, we obtain, okay, again after applying the Gauss law, we obtain, I will give you the formula to be understood in a better way. Let us consider, I'll give you two important cases here, and both are very, very important cases. Okay, for numerical also and direct for factual questions also. We have observed that in GATE as well as in engineering services, there have been, direct questions from this concept. The electric field due to a solid sphere, electric field due to a hollow sphere. Both I'll just cover up here, right? So suppose if it is a solid sphere. Okay, just a moment. Suppose. Able to get that. Just a second, guys. No. Okay, chalo, no issues. We'll continue regularly. Yeah, so suppose if it is a solid sphere, sorry for the interruption. Okay, suppose if it is a solid sphere, a sphere which is filled uniformly with the charge q throughout its volume. Okay, every part on the sphere and inside the sphere is filled uniformly with the charge q. Okay, just don't mind the drawing right now. Let's go quickly. And suppose this is the center of the sphere. Okay, what is the electric field at a point which can be inside? Achha, what is the radius of the sphere? Let me highlight the radius. Radius, as I have told you, radius here is equal to a. Now, suppose there is a point P which may be point inside, or there is a point P which can be outside the sphere. What is the electric field at these points? At a point inside or at a point outside the sphere? Very simply, guys, first of all, remember what is the electric field inside the sphere, electric field outside the sphere. Chalo, simply let me give you the electric field outside the sphere. Right, the electric field outside the sphere is actually given by the formula kq divided by, suppose this distance is r, kq by r square. Kq by r square, and that is just like point charge. This is also the electric field due to a point charge also. So what you can imagine is, suppose the total charge carried by the sphere is q, and suppose if it was just a point charge q located at the center. Suppose there was no sphere, there was only a point charge having the same magnitude of charge q, and that was located at the center of the sphere. Then what is the electric field of point charge? Kq by r square, r is the distance. So electric field at any point outside the sphere is just like the point charge. What about inside? At a point which is inside, electric field is proportional to the r. R is the distance of the point of observation. First of all, the very important point you should remember is electric field is proportional to r. Higher the value of r, more you move away from the center, more charge you accumulate and more electric field you get. More electric field you get, and it is actually given by the formula. It is actually given by the formula, as I've just told to you. It is r upon 3 epsilon, or epsilon naught if it is free space, rho v. Right, so it is r divided by 3 epsilon rho v. Okay, if it was a hollow sphere, then guys, suppose if it was the case of a hollow sphere, if it was suppose the case of a hollow sphere, where only the surface of the charge, only the surface of the sphere carries the charge, only the surface of the sphere carries the charge, and inside it is hollow, it is blank, the radius is still equal to a. And once again, let me take the point of observation P, which can be inside or which can be outside. What is the electric field at these 2 points? What is the electric field at these 2 points? So very logically you can say that electric field, always remember guys, whether it is hollow, solid or hollow, electric field outside is simply given by the formula just as point charge. So kq by r square, r is the distance from the center of the sphere. But what is the electric field which can be inside? Now inside there is no charge, the only charge is available on the surface of the sphere. So I can say that inside there is no source over this portion, and that is why the electric field inside the hollow sphere at any point should be 0. At any point should be 0. At any point must be equal to the 0. Okay. Next, you can expect the questions on very important electric potential. Okay, so next are the questions that is going to be related with the electric potential. Okay, so to understand electric potential or work done, these are two areas where questions are again expected. So you know, let's write down first the formula of work done and then the formula of potential. And the situation is something like you have a point charge located at the point A and you are trying to move the point charge towards the point B. Okay, towards the point B. What is the work done? What is the work done? So see, work done is actually if you move the point charge from A to B, forget A to B, let's consider a very small displacement of the charge, and that small displacement is given by the length dl. Okay, suppose you move the point charge through a small length dl. So what is the work done? It is given by F dot dl. The work done is F dot dl. Okay, so minus of F dot dl, we'll talk about the significance of minus sign separately. So what is the total work done in moving the charge from A to B? Now, what is the force acting on the charge in the presence of electric field? That is Coulomb's law. Force is Q into E. Electric field is force per unit charge and force is equal to Q into E. Right. So what is the small work done in moving the particle through the small length dl? It is minus F dot dl and F is equal to Q into E according to the Coulomb's law. So what is the total work done? The total work done or the total potential energy required in moving the charge from point A to B, it is the integration of the previous case. Integration from what? From point A up to the point B. The integration from point A to the point B. So work done is given by minus Q integral A to B integral E dot dl. Line integral form. This work done, if it was a unit charge, if it is a 1 Coulomb of charge, then what is the work done? It is minus integral E dot dl from point A to point B. The work done in moving 1 Coulomb of charge, right? Or we can say that work done per unit charge in moving the charge from the point A to the point B is known as the potential difference between the points A and B. Is known as the potential difference between the points A and B. So this is again next important formula where questions are expected for you. The potential difference between points A and B, it is minus integral E dot dl. Minus A to B integral E dot dl. Okay, so next area where questions are expected. Line integral. It's indirectly a line integral question. Okay, the work done is minus integral A to B E dot dl. Indirectly a line integral question. Minus integral A to B E dot dl. Right. Okay. Achha, how do you calculate the absolute potential? That also let us discuss. The absolute potential of any point. Absolute potential of any point is given by the formula simply KQ by R. Let's write it as simple KQ by R, and then the potential difference can be written as VB minus VA. Second point minus first point. Right. Potential difference between 2 points. What was the potential difference between 2 points? It is the work done in moving 1 Coulomb of charge. That is unit charge. Work done per unit charge for moving the charge from A to B. From A to B. That is the potential difference between A to B. What is the absolute potential? Absolute potential is just like work done in moving the charge. Okay, work done again per unit charge, of course. Work done per unit charge in moving the charge. How much is the work done? In moving the charge from the reference point, which is commonly taken as infinity, from infinity to the point of observation P. From infinity to the point of observation P is known as the potential at that particular point. So how do you actually calculate? Let us understand with a simple picture. Suppose this is the point charge Q. Okay, and you are interested in measuring the potential at this point P, and this is my point of observation. Okay, what is the potential at the point P? Okay, so we all know that potential being a scalar quantity, you only need the distance of the point from Q. Okay, and the potential at the point P is simply given by the formula, as I told you, KQ by R. It is simply given by the formula KQ by R, where R, only this one, and this is again a very important and expected question producing area. KQ by R. What is R? It is the magnitude of the vector R, right? Magnitude of the vector R. That means it is the distance. Again, let me say that this point charge is available at some point A, It is available at some point A. So this means the length of the line QP, the length of the vector QP, that you can easily calculate using the distance formula. Here you only need the distance. You don't need any unit vectors. You don't need any vector, because potential is the scalar quantity. Okay, potential is the scalar quantity. Okay, the equations del cross E, the next of the second Maxwell's equation for us as per today's discussion. Okay, the number 2 Maxwell equation for us, that electric field is conservative. No derivations, no proof, everything has a simple proof, but we have to just go in a F1 form, revising the formulas. So del cross E equal to 0. This is the second Maxwell's equation, okay, for static fields. Right now we are first summarizing the Maxwell's equation for static fields. Electrostatic fields, del cross E, conservativeness of the electric field. Okay, the electric field is conservative. Del cross E is equal to 0, or the line integral of electric field along a closed path is equal to the 0. Okay, the line integral of a electric field along closed path is equal to the 0. Also, this is related to the concept. This is also related to the concept that potential difference, better I'll write down here, the potential difference, just let me take an extra slide. The potential difference, guys, VAB does not depend, VAB does not depend on the path, does not depend on the path joining A and B, right? It only depends on initial and final points. Initial is A, final is B. It only depends on initial and final points, right? So VAB, what is the VAB formula? It is minus integral E dot dl, and that is independent of path. The line integral is independent of path. Line integral is independent of path, and as per the vector calculus theory, if any line integral is independent of path, then the vector whose line integral you are calculating, then the vector is conservative. Achha, why it is independent of path? That derivation we are not looking into right now. Okay, so electric field is conservative. What is a conservative vector? A vector whose curl is equal to 0. A vector whose curl is equal to the 0, and that is what we have written as the final Maxwell's equation number 2 for the static fields, right? Okay, and then according to the Stokes theorem, this also can follow. Okay, Achha, what is the relation between electric field and the potential? Already I have briefed you in the beginning also. Electric field is negative of the gradient of V, and due to this equation only we say that electric field is in a direction opposite to the direction in which V increasing, right? Because if V is increasing, this is the rate of change of V, space rate of change of V, right? So if V is increasing in this space from some point A to some point B, its rate of change, its gradient will be positive, but electric field is in minus of that direction. So if potential is increasing in this direction, electric field should be pointing in the opposite direction, and that is why we say that electric field flows from higher to the lower potential. Okay, opposite to the direction in which V is increasing. If V is increasing this way, electric field is in the direction of V decreasing, that is higher to the lower levels of V. Okay, the next two important equations where questions can be expected is the Poisson's and the Laplace equation. Del square V is equal to minus rho V by epsilon. That is the Poisson's equation. Rho V is the volume charge density, and if the medium is charge free, if the region is charge free you are considering, rho V will be 0, and then the del square V is equal to the 0. That is what is known as the Laplace equation. These are again two next important equation, that is the Laplace equation and the Poisson's equation. What is del square, guys? चलो यहाँ पे separately लिख देते हैं. Del square is known as the Laplacian operator. Del square is known as the Laplacian operator, and the value of the del square in the regular Cartesian coordinates will be del 2 by del x square, del 2 by del y square, plus del 2 by del z square. Del square, which is represented as the dot product of del with itself. It is del dot del. It is a dot product of del with itself, del dot del, and that is known as the Laplacian. That is known as the Laplacian operator, right? Okay, that is what is a Laplacian operator. Okay, and we have the Poisson's equation and the Laplace equation. Just a moment, guys. Yeah, chalo. Let's continue. Let's proceed with the discussion. Okay, this is the Laplace and the Poisson's equation. What is the energy density in the electrostatic field? That could be the next case, but this is not very important. No, with the numericals, this formula may not be important. Right? Hi Raghu. Okay, this will not be important. So if there are n point charges available in a medium, the total energy is given by, how do we calculate? Not required. Anyways, this is not important also. Even the final formula is not much important. It is just given by half summation of qk vk. It's like q1 v1 plus q2 v2 and etc. Half the summation of qk vk. If the medium is having continuous charge distribution, then it is given by half epsilon e square. This is the volume charge density. Okay, this is the volume charge density. Sorry, I mean this is the energy density. Okay, we, small w is the energy density, that is the energy per unit volume, joules per cubic meter. Okay, so how do you calculate the total energy? Let me write down. Again, these are not important formulas for numerical. This is known as the electrostatic energy density. Energy per unit volume, that is given by half epsilon e square. E means the magnitude of the electric field, and we, this we, capital we, is the total electrostatic energy. And to of course calculate the total energy, okay, we can volume integrate the energy density. We know the energy per unit volume. Let's calculate the energy for the entire volume by performing its volume integral. So we get the total electrostatic energy. Okay, electric dipole, moderately important. Okay, all the topics before this were very, very important. Electric field, Coulomb's law, electric potential, Gauss law, the concept of flux, the 2-3 formulas related to the potential, very important, but these are moderately. Energy density, the very, very less important. Dipole, moderately important, I can say, for numerical point of view. Dipole is important as a concept. Okay, but hence now we are revising formula, so not directly important for numericals. Moderate important, I will say, for this particular topic, electric dipole. Okay, first of all, for any electric dipole, note down its dipole moment. How do we define the dipole moment of electric dipole? The dipole moment of the electric dipole is simply defined as QD. The QD, where Q is the magnitude of the charge. Which charge, sir? So what is the electric dipole? Electric dipole is formed when you clearly take 2 point charges of equal magnitude. 2 point charges of equal magnitude, Q and minus Q. Okay, but opposite sign. So both the magnitude are same, but they are of opposite sign, and they are separated by a very small distance d. So d is the distance between the charges. So what is Q? Q is the magnitude on the charge, and d. How do you represent d? Let me write down this as d. Just a second. D into AD cap. Yeah, for this picture, that is AZ cap. Okay, D is the magnitude of the distance between the charges. D, it is the magnitude of the distance between the charges. What is AZ cap? AZ cap is a unit vector from the negative charge to the positive charge. So right now this dipole has been arranged along the z axis. It may not be always from the z axis. So let me generalize and say this represents the unit vector. This is actually representing the direction in which the dipole is placed. So this is the unit vector, okay, from minus q towards the plus q. Unit vector from the minus q towards the plus q. unit vector from the minus q towards the plus q. It is the az cap, and the dipole moment is qd. The qd, d is known as the location vector. Overall we call this d as the location vector. Okay. Now again, after applying the formulas that I have briefed you for potential, we get the answer as qd cos theta upon 4 pi epsilon r square. What is the cos theta? Theta. Okay, so this is some point of observation. We are measuring the field at point of observation. Theta is the angle subtended by that point of observation from the center of the dipole. It is the angle subtended with respect to the center of the dipole. Okay, what is r? R is the distance of the point of observation from the center of the dipole. From the center of the dipole. Okay, we get the potential at any point due to this dipole as qd cos theta divided by 4 pi epsilon naught r square, or again you can write this as kqd cos theta divided by r square, right? Kqd cos theta by r square. In the vector terminology, okay, dipole moment anyways I have defined. In the vector terminology, this is also written as kp dot ar cap divided by r square. K is 1 upon 4 pi epsilon naught, as we always call it as, or simply 1 upon 4 pi epsilon if it is not the free space. Okay, definitely if you take the plane z equal to 0, which is midway between the two charges. Okay, so if you take the plane which is midway, that is the xy plane. If you take any point here, suppose on the y axis, x axis, or anywhere on the xy plane, okay, and you join it here. Yeah, if you measure just the theta, what will be the theta? Okay, if you take the point of observation here, how much the theta becomes? Theta was the angle with respect to z axis, the colatitude angle, and this is clearly becoming 90 degree. If the theta is 90 degree, dear, if the theta is 90 degree, what about the cos theta, right? If the theta is 90 degree, then you will have cos theta, cos 90 as 0. So at any point on the xy plane, theta is 90, and then the cos 90 is 0, and that is why the potential at any point will be 0. Okay, potential at any point is 0. So whatever is the plane, right here it is xy plane, in general it could be anything else, any plane which is midway of the dipole, any plane which is midway of the dipole is always at equal potential, and that equal potential is 0. That is known as the zero equipotential curve. That is known as the zero equipotential curve. Now we know the potential, we can calculate the electric field. Now up to the potential it is okay. It is, I told you already, this is moderately important. Remember the formula maximum up to the potential. This one, okay, maximum potential ka formula yaad rakho, either in terms of dipole moment or either in terms of the qd cos theta. But electric field is calculated as negative of the gradient of V. Okay, here V has been represented as P dot AR, where AR is the unit vector in the spherical coordinate system. So we apply the gradient formula as per the spherical coordinate system, and this is the electric field finally obtained. This is not even moderately important. So this is something you can, compromise and you can skip. This is not much important for you. This portion is not much, electric field is not much important for you here. Okay, the method of images, this is important. The method of images. What is the method of images? Okay, rather than explaining you the theory and procedure, let me explain you. For this particular topic, I'll take a question to explain you the thing. Okay, for this particular topic, I'll take you the question and then I will explain you the thing. Okay, it's better to understand this with the help of question. Hi all, good evening. Right everyone, so let's take a question and understand the method of images. The question and the method of images. Right. Look into this. A perfectly conducting metal plate, okay, a perfectly conducting metal plate is located in the xy plane. It is placed in the xy plane in right-handed coordinate system. So see, a perfectly conducting metal plate. Whenever there is a question that is coming on a conducting plate, okay, on a conducting plate, you have to think about the method of images. Okay, you have to think about, this is the area where you have to think and apply the method of images when there is a perfectly conducting metal grounded plate. Okay, this is placed in the xy plane in a right-handed coordinate system. A charge of 32 pi epsilon naught root 2. Let's say this is some charge q. Let's say this is some charge q is located at the coordinate 002. It's located at the coordinate 002. At the coordinate root 2 comma 0, that is this coordinate xy0, z0, and that is the xy plane. At the coordinate root 2 0, what is the electric field? What is the electric field? Now all dear students, you know and you can calculate the electric field You can calculate the electric field due to this particular charge, which is at 002. But what is the electric field due to the metal plate? For that itself, we apply the method of images, and according to the method of images, now understand the method of images here. I told you for this only question is better to explain you this. Okay. So what is the scenario right now? What is the scenario right now? That you have a conducting metal plate and you have a charge. You have a charge which is plus Q. Okay, and there is a conducting metal plate. According to the method of images, this will be equivalent if you remove the metal plate, assume it as a mirror, and the role of the mirror is to create the reflection. There is the charge plus Q and the mirror charge, the image charge, which is known as the minus Q. This is known as the image charge. So replace that metal plate, replace this particular metal plate, right? Replace this metal plate and place an image charge which is same magnitude as Q but opposite in sign. So whatever is the source, guys, which is above the metal plate, you have to place another source below the metal plate at the very same distance. So distance को भी highlight कर देते हैं. At the very same distance. So suppose this was the distance which is equal to D. So the image charge that you place, the image charge that you place should also be at the distance. If this is D, this should also be D below the metal plate. This should also be D below the metal plate. Okay. This is what is the method of images. This is how you apply the method of images. Now let's apply to this particular question. Okay, to this particular question. So there is a charge of 32 pi epsilon naught root 2. We'll call it as plus Q only. That is at 002. And where is the plate? XY plane. Okay, so 002 means how much is this distance? This is equal to 2 units. Okay, so where will you place the image charge? 2 units below. Where will you place the image charge? 2 units below. Okay, let's take this picture here separately. Let us take this particular picture here separately. There is a point of observation. Just a moment. Okay, redraw that. There is the point of observation which is on this particular sheet. Okay, that is root 2, 0, and there is a charge at the point 002. That is the charge plus Q. By applying the method of images, this is the point of observation which is root 2, 0. This is suppose some point A. As per the method of images, I will place another image charge. Which is minus Q, and suppose that is the point B, but that should be 0, 0, minus 2. If it is plus 2 above, here it should be minus 2. We need to calculate what is the electric field at the point P. So electric field at the point P will be obtained as the vector sum of the electric field due to the charge plus Q and due to the charge minus Q. This is now my point of observation, and what is the electric field at this point? That is the question. Let us calculate the electric field at this point as the electric field E1 plus electric field E2. And to calculate electric field, in the very beginning I told you that we need electric field in the vector form. So what is the vector from the source to the point of observation? Let's say this is the vector R1. What is the vector from the second source to the point of observation? Let's say that is the vector R2. Right. So what is the vector R1 here, dear? The vector R1 is the vector from point A to point P. Okay. The vector R2 will be the vector from point B to point P. From point B to the point P. Let us calculate these vectors first of all. Let's be handy in calculating these vectors. Okay. So first let us calculate the vector R1 individually. So what is that vector R1? AP is given by P minus A, second minus first, right? P minus A. So root 2 minus 0 will be root 2 in the x direction. Root 2 minus 0 again will be root 2 in the y direction. Corresponding x to x component subtract, y to y, z to z. Z to z, 0 minus 2 will be minus 2az. Okay, this is the vector R1. Simply, this is known as the vector R1. So what is the length R1? Length R1 means magnitude of R1. What is going to be its magnitude? That is square root of x square plus y square plus z square. And that becomes 2 plus 2 plus 4. That is square root of 8. that is square root of 8, 2 root 2 or square root of 8, right? Similarly guys, we can calculate what is the vector R2. Better let me remove this from here. Okay, just keep on focusing. What is the vector R2? Vector R2 is the vector from B to B. Okay, B to P. Yeah, I'll share you the link, Bhaskara, just wait for it. And that is the vector from B to P, and that is P minus B, position vector of P minus the position vector of B, right? And again, P, root 2 minus 0, x to x component subtract, root 2 ax, okay, then root 2 ay, 0 minus minus 2, it will be plus 2 az here, it will be plus 2 az, right? And what is the length R2? It is the magnitude of R2, and that will be square root of again root 2 square plus root 2 square plus 2 square. Root 2 square plus root 2 square plus 2 square, that is again root 8, or that is equal to 2 root 2. Okay, now this is, as I told you, this is the point of observation. We need the electric field at the point of observation, and that can be obtained by the superposition concept, E1 plus E2. Okay, now let us apply this formula. So here you are indirectly understanding the electric field calculation also, and as well as you are calculating, you are looking into the electric field E. So electric field E is equal to the E1 plus E2. The electric field is E1 plus E2. What is E1? K Q1 upon R1 square unit vector AR plus K Q2 upon R2 square unit vector AR2. Here it should be AR1. Acha, what is the unit vector? If you write down unit vector, it is a vector divided by its own magnitude. So it will become cubic equation then, as we have learned earlier also. So this becomes KQ by R1 cube vector R1 plus K Q2 by R2 cube into the vector R2. Now let us place the value. Let us place the value of Q1 and Q2. Right, Q1 and Q2. What is the Q1? It is Q. What is the Q2? It is minus Q. Right, accordingly if we place na, इसको remove करके accordingly let me place the charge itself here. This is charge plus Q. This one is the charge plus Q, and Q2 is the charge which is known as minus Q. Okay, what is the K? K is 1 upon 4 pi epsilon naught, right? What is the Q? What is the value of Q? 32 pi, कहाँ चला गया? 32 pi epsilon naught root 2. 32 pi epsilon naught root 2. This is the value of the charge. Vector R. Now what is the vector R? Root 2 ax, root 2 ay, minus 2 az divided by 2 root 2 whole cube, minus kq is outside, minus you get the vector R2 which was 2ax, sorry, root 2ax, root 2 ay, 2 az divided by again 2 root 2 whole cube. Okay, so just keep noticing 4 pi epsilon naught, 32 pi epsilon naught cancelled, you have 8 root 2 divided by 2 root 2 whole cube. It's like root 8 ka cube, so root 8 ka square karenge to 8 hoga, and then you have one more root 8, that is 2 root 2. So this is 8 root 2 upon 8 into 2 root 2. Numerator, when you subtract the vector, root 2 minus root 2 cancelled, root 2 ay minus root 2 ay cancelled, you are left with minus 2 az, minus 2 az, so total minus 4 az. Minus 4 az. Okay, 8 cancelled, root 2 cancelled, your answer is minus 1 by 2 az. Something like this your answer is coming up. Minus 1 by 2 az. 8 cancelled, root 2 cancelled, sorry, minus 2 az actually, 4 by 2. So the answer is nothing but minus 2 az. Your answer is equal to the minus 2 az or minus 2 k direction. Az is a unit vector along z direction, which is also known as the k cap. The unit vector is ijk. The answer is minus 2. This is how you apply the method of images, guys. Okay, so for method of images, we had to take a question only. There was no other call but to take the question only, right? Hello guys. Yes, is it now fine? Yeah, I think there was some issue. Is it now fine? Quickly confirm everybody. Quickly just confirm everybody. Is the video fine now? Yes, I think it got stuck. There was some issue. Is it fine now, guys? Quickly confirm me once. Now okay, chalo, cool. So let's get moving ahead then. Okay, let us get now moving ahead with some topics of the magnetostatics, starting with the very basic and very famous Biot-Savart law, which states that the differential magnetic field, a small magnetic field due to a small current element, a differential current element IDL, which carries the current I and having the very small length DL, okay, which carries the current I and having some small length DL. It is, even smaller than this, but just to show you the picture, this is the current element considered. There is a current element IDL carrying the current I and having the small length DL. What is the magnetic field at the point of observation? At the point of observation due to any differential current element? So that magnetic field DH is actually proportional to IDL. According to Biot-Savart law, this is proportional to the current element IDL. This is also proportional to the sine of the angle between the current element and the line joining the point of observation. Okay, so you take a line from the current element to the point of observation. What is the angle subtended by this line with respect to the current element? That is alpha. And this magnetic field, again as expected, is inversely proportional to r square. Higher the distance, lesser is the field strength. A DH is proportional to 1 by r square also. Okay, so it is proportional to the ideal, it is proportional to the sine alpha, and it is proportional to the 1 upon r square. And accordingly, we have DH being proportional to ideal sine alpha by r square. Right, yes, even on the signals. Next week, relax. The Formula 1 series of signals will also come up, and it will be in two different parts. Okay. So DH is equal to K ideal sin alpha by r square. K is the constant of proportionality whose value was calculated in the SI units, and it is obtained as 1 upon 4 pi. This is the very basic Biot-Savart law. Okay. Now this particular form, since sin theta is involved and sin theta comes in the cross product, so this DH was also written in the form of cross product. Ideal cross AR by 4 pi r square. What is AR? So see, this is the vector R, right? This is the vector R, vector from the source to the point of observation. So what is the unit vector AR? The unit vector AR is of course the vector divided by its length, divided by the length R. Okay, so it is ideal cross AR upon 4 pi r square, or it is ideal cross vector R divided by 4 pi r cube if you write down in terms of the vector R. In terms of unit vector, this is the formula. Okay, now since cross product is involved, how do you find out the direction? We will come see. This is just the beginning of Biot-Savart law. When what is the formulation of magnetic field of different sources due to Biot-Savart law or due to Ampere's law? Ampere's law will also come. We'll brief that formulas as well. But since cross product is involved, what is the direction? It is given by the right hand thumb rule. It is given by the right hand thumb rule. Okay, so if suppose this is the wire carrying the current, if this is the current element carrying the current I, what is the magnetic field due to it? It is given as per the right hand thumb rule, and it simply says that place the right hand thumb, place your right hand thumb in the direction of current. So let's say current is in the upwards direction. Place the right hand thumb along the direction of current. The curl of the fingers, the rotation of the fingers will tell you the direction of magnetic field. So how are the fingers rotating? Fingers are rotating in a circular path around the axis of the wire. Let's say the axis is Z direction. For a moment, let's assume this is the Z direction. So what is the circular direction about the Z axis known as? Cylindrical coordinate system is what you have to recall. Circular direction about the Z axis, about the axis of the cylinder, is known as the azimuthal direction. So this will be the phi direction. So if the current element is in the Z direction, we have the magnetic field in the phi direction. Or in direction, in general, we can say magnetic field will make the circular path around the axis of the wire in accordance with the right hand thumb rule, or also you can test by the right hand screw rule. This is the right hand screw rule, which simply says that try to tighten up a screw. Suppose you are fastening a screw. In which direction? Fasten up the screw in the direction in which current is there. So as I told you, current is suppose in the upwards direction. So in this direction, I will fasten up the screw. What is the direction traced by the circular tip of the screw? ये जो tip दिख रहा है ना, the direction traced by this circular tip of the screw will be the direction of the magnetic field, which is again in the form of circular rings around the wire. Right, that is the direction of the magnetic field actually. Okay, now after the application of Biot-Savart law, we calculate the magnetic field due to a straight current carrying filamentary conductor. What is a filamentary conductor? Filamentary conductor is a wire which is very thin actually, something which is very thin. I mean the length of the wire is much greater than the dimensions, than the diameter of the wire. Okay, so if you have a straight current carrying filamentary conductor, very thin conductor of finite length, okay, which is placed from point A to the point B. A is the starting end of the current, B is the terminating end, okay, and we have a wire of finite length. What is the magnetic field? It is given by the formula after the application of Biot-Savart law. This has been calculated and it is given by the formula I upon 4 pi rho cos of alpha 2 minus cos of alpha 1. I divided by the 4 pi rho cos of alpha 2 minus cos of alpha 1. So guys, what is alpha 2, what is alpha 1, what is I, what is rho? This is a very important formula. Let me explain you this one separately, okay, rather than the previous picture. Isko separately samajhte hain. Okay, suppose this is what is the current, this is what is the wire, filamentary wire. Everybody just assume so that I don't have to hide. Suppose this is what is the filamentary wire, okay, placed from A to B, and the current is flowing from A to B. Current is flowing from A to B. This is my P. This is the point P, which is known as the point of observation. Okay, this is the point P, which is known as the point of observation. Now everybody understand the formulas. What is alpha 2, what is alpha 1, what is rho, everything let me explain you here. First of all, join the point of observation from both the ends of the wire. Right? From both the ends of the wire. Alpha 1 is the exterior angle with respect to starting end. So where is the current starting? It is starting from A. So what is alpha 1? I'll write down here for a clear picture. Alpha 1 is known as the exterior angle. Important formula ये है, with respect to the starting end, from where the current starts. What about alpha 2? What about the alpha 2? Alpha 2 is known as the interior angle. Alpha 2 will be measured as the interior angle from where? Look at this. From the ending end, terminating end. Yeah, simply let me write down the ending end with respect to the ending end. Ending means where the current ends. The current is flowing from the point A to the point B. Okay. Now, I is the current carried by the wire. That is very logical. Divided by 4 pi rho. And the direction is A phi. What is rho? So, rho means the perpendicular distance of the point of observation from the axis of the wire. Right? So if I join the point P from A or from the B, we are not getting the perpendicular distance. So that is why I extend the axis of the wire. Perpendicular distance from the wire nahi bola. Perpendicular distance from the axis of the wire. Anywhere from the axis of the wire, you need the perpendicular line. So this is what is the perpendicular line. Okay. Let me redraw this. You need the perpendicular line here from the axis of the wire to the point of observation, and the distance of this line is known as rho, and the direction from the axis of wire to the point of observation is represented by the unit vector that is known as a rho. Okay, so rho is the, what is the rho? Let me write down rho also here. It is known as the perpendicular distance from the axis of the wire. Perpendicular distance from the axis of the wire. The direction of the magnetic field is given by A phi. What is A phi? A phi is evaluated as AL cross A rho. What is AL? What is A rho? Right, A rho, it is the direction along the perpendicular line. It is direction along perpendicular from axis of the wire to the point of observation. Perpendicular from the axis of the wire to the point of observation, this direction. Okay, the line which is used to calculate rho, the perpendicular distance, the direction of that line is A rho, right? What is AL? So AL is known as the direction in which the current flow. So AL will be known as the direction of current flow. AL will be known as the direction of the current flow, dear. This is known as the direction of the current flow. This is known as the direction of the current flow, right? This is known as the direction of current flow, right? So AL cross A rho, and H is equal to I upon 4 pi rho cos of alpha 2 minus cos of alpha 1. Alpha 1, alpha 2 rho, everything I have explained with you. Okay. Right. So these are some important points. This formula is applicable for any conductor. Okay, not necessarily on z axis, but it should be straight. We have talked about the straight conductor. Okay, semi-infinite important nahi, but this infinite in length is important. When the conductor is infinite in length, actually this formula is very, very important for you. Okay, long conductor. Most of the questions are usually based on conductors which is of very large length, infinite in length. And after putting the required value of alpha 1, alpha 2, let's not derive the final important formula for you. I upon 2 pi rho A phi, where I told you A phi is actually calculated as AL cross A rho. AL cross A rho. Okay, AL A rho both are described as I've already described for you. Okay, so these are the important points to be noted from this formula. Okay, let's have a quick recap of the Ampere circuital law, and that is going to be your next Maxwell's equation for today. So actually number 3rd for today. Okay, already I have briefed the 2 Maxwell's equation for static field. Finally, I will conclude with the time varying final Maxwell's equation also. The Ampere's law, which says that the line integral of H, circulation of the magnetic field around a closed path, is equal to the net current I enclosed by the path. Integral H dot dl is equal to I enclosed, and then we can apply the Stokes theorem on the left hand side, because line integral along a closed path can be simplified as Stokes theorem. Okay, when you apply the Stokes theorem, okay, you are finally going to get this relation. Let's have a look at the final formula. So del cross H is equal to J. Now this is the area where questions are more expected. यहाँ से question ज़्यादा बनता है. Given a magnetic field, calculate the current density of the medium. That is given by del cross H. Del cross H. J is the current density of the medium. What is J? Current density, or the conduction current density of the medium. J is the conduction current density of the medium. That is the conduction current per unit area. It is measured as current, that is ampere per unit area, that is meter square. Ampere per meter square. Okay, so we have both the form of the Maxwell's equation, integral and differential form, but although for questions always in differential form will be more relevant, more frequent with the question, but both the forms you must remember. This is the next Maxwell's equation, but related to the static magnetostatic field, static magnetic field in short. For time varying fields, there will be a change in Ampere's law. What we say, a correction term, that is a displacement current density, has to be added. We'll go to that also. Okay, so this is the basic Ampere circuital law, right? And then again by Ampere circuital law we can calculate the current even due to the previous case. We can apply the Ampere's law to calculate even what is the magnetic field due to a wire of finite length. This also can be simplified easily. Next formula, if the entire sheet, a sheet of current, once again I tell you, there's nothing like infinity. A sheet, infinite sheet of current means a very long sheet. Okay, if this sheet becomes very, very large, a sheet of infinite extent, a very large extent, okay, located in xy plane or any other plane, the final field is given by, forget this, just remember this formula. Isko hata do. What is important for you, what you have to finally remember. So if there is an infinite sheet of current having the current density K in ampere per meter, okay, K ampere per meter, then its magnetic field is simply given by half K cross AN. Half K cross AN. What is the AN? What is the AN cap? Unit vector. Unit vector normal to the sheet. It is the unit vector normal to the sheet. It is the unit vector normal to the sheet. Half K cross AN cap. Unit vector normal to the sheet. It is the unit vector normal to the sheet. Similar to the electric flux density, we define the magnetic flux density. Electric flux density was related as D is equal to epsilon E. The concept of flux anyways I have briefed you. Okay, so let us go with the final formula. We have the magnetic field, magnetic flux density B is equal to mu naught into H. B is the magnetic flux density. Mu naught is as always the permeability of the free space. So if you want to calculate the total magnetic flux, that is the surface integral. That is the surface integral of B. So total magnetic flux will be surface integral B dot ds. The unit of the magnetic flux is actually Webers. So what is the flux density? Flux density, flux per unit surface area, that is Weber per square meter. That is also commonly known as Teslas. That is also commonly known as the unit of Tesla. Okay, this is the flux crossing any surface. But what is the magnetic flux crossing any closed surface? If I take any closed surface, here you get the next Maxwell's equation. Okay, there is a concept of magnetic monopoles, that magnetic monopoles cannot exist. Till date, there is no proof of existence of magnetic monopoles, although research is still going on. Okay, But by the concept of absence of magnetic monopoles, we get that the total flux crossing any closed surface is always zero. Because any closed surface will enclose a magnetic dipole. There is no magnetic monopole. I'm not proving, I'm just giving you the oral statement and the final formula as for the F1 series. Okay. But any closed surface will always enclose a magnetic dipole because there is no magnetic monopole ever possible, and that is why the total flux, okay, is equal to zero. Once again, you apply the Gauss divergence theorem, surface integral over a closed surface. Now, Gauss divergence theorem you apply. According to Gauss divergence theorem, this becomes integral del dot B dV, the volume integral of the divergence of B, and this means that del dot B itself will be zero. So what is del dot B? Is zero. What is the del dot B? That is equal to zero. That is the final fourth Maxwell's equation for you for today. In sequence, that is the fourth Maxwell's equation. Let me give you a quick briefing in front of you. What are the four Maxwell's equations you have seen till this time? What are the four Maxwell's equations you have seen till this point of time? Okay, till this point of time. Okay, let me hide myself. Okay. Yes. So Gauss law, del dot D is equal to rho V. Okay, and this is the integral form. As I just now told you, absence of magnetic monopoles will give you the Maxwell's equation del dot B equal to zero. Just now we have seen. Okay. Conservativeness of electric field. The potential difference between any 2 points is independent of the path. Line integral of electric field is independent of path. Del cross E is zero. And then the Ampere's circuital law. Del cross H is equal to J. Del cross H is equal to J. These are the four Maxwell's equation for the static. Please remember this important word. Okay, for the static electric and magnetic fields. For the electric and magnetic fields which are not dependent on time, which are independent of time. They are a function of only space but not of time. Okay, static, electric and magnetic field. These are the Maxwell's equation. What are the final Maxwell's equation for the time varying fields? Usko bhi hum brief karte hain. Right. Let me also add on one more terminology here. That is the magnetic vector potential. Okay, like we have the electric potential which is scalar, we have the magnetic vector potential. Okay, B is equal to del cross A, where A is known as the magnetic vector potential. A is known as the magnetic vector potential measured in Weber per meter. Okay, this A is known as the magnetic vector potential. So given the magnetic vector potential, you can calculate the B as the curl of the magnetic vector potential. Curl of the magnetic vector potential, right? Okay. Right. The next thing that you can relate, from where you can expect the question is due to the forces on a charged particle when it is moving in the presence of electric field or magnetic field or combined electric and magnetic field. What is the force due to magnetic field? The force on a charged particle due to the magnetic field is given by the formula actually Q into U cross B, where U is the velocity of the particle, and if the particle is stationary, okay, if the U is equal to 0, the magnetostatic force will also be 0. That simply says that a stationary particle will not experience any force in the presence of magnetic field. So only a moving charged particle can experience a force in the presence of magnetic field, and that is given by, oh sorry, this is a typo error. It is given by Q into U cross B, right? So if it is a stationary particle, it can experience the force only under the presence of electric field, not in the presence of magnetic field. But if it is a moving charge particle, it will experience, of course, the electrostatic force and also the magnetostatic force. Okay. So what is the total force then? What is the total force then? The total force on a moving particle in the presence of both electric and magnetic field is the addition of them, QE plus QU cross B. Okay. And this total force equation, this net force or the total force equation, is what is known as the Lorentz force equation. Okay, so for a moving charge, this is applicable only for moving charge, because for a stationary charge only Fe will be there. So for a moving charge, the total force will be given by Fe plus Fm, or that is QE plus QU cross B. Q has been taken common. This is known as the Lorentz force equation. Total force on a moving charge in the presence of both electric and magnetic fields. Right, in the presence of both electric and magnetic fields. Acha, if let me tell you one more important point with respect to magnetic field, Fm, which is given by Q into U cross B. Right, some important conclusions regarding to the trajectory of the particle. Right. Case number 1: if the particle moving with a velocity parallel to the B field, parallel to the B field. We know that if U and B are parallel, Fm will be 0. F is mass into acceleration. Acceleration is rate of change of velocity. When we solve this and put it equal to 0, net force to 0. When we put this equal to 0, we get the trajectory of the particle, and the particle is going to move in a linear motion. Particle will follow linear path, linear motion. The particle will be moving in a linear motion. The particle will be moving in linear motion. Number 2 point, if the velocity of the particle is perpendicular to the B field, then the particle will be moving in the circular motion. Okay. They are very, very simple proofs, but not required to prove right now. Okay. We can prove it using F is equal to m into a and a is equal to du by dt. Acceleration is rate of change of velocity, right? Right. So if the particle is moving parallel to B field, it will follow linear motion. If the particle is moving perpendicular to B field, it will follow a circular motion, right? Follow a circular motion. So if U is both parallel and perpendicular to B, right, then it will follow circular motion also, linear motion also. So just stretch a circle along a linear path, what you get is a helix. What you get is a helix, and the particle then follows a helical path. Then the particle is moving in a helical motion. This was once a gate question. IISc Bangalore designed this. Okay, right? IISc Bangalore designed that. These are some simple cases that you must be directly remembering. If the particle is moving, yes, particle is having a velocity, one of the component parallel, one of the component perpendicular to the B field, right? Okay, the Faraday laws. The Faraday law. Okay, according to the Faraday's law, let's quickly recap the formula related to Faraday's law as well. Faraday's law of electromagnetic induction. Faraday stated that a static magnetic field produces no electricity, produces no current flow, but a time varying magnetic field produces an induced voltage, which is known as the EMF simply, in a closed circuit, and that causes a flow of current. So a time varying magnetic field induced can produce electricity. This was one such apparatus used by Faraday. Let me hide myself. There were several. See, whenever there is a rule, there is a law coming up as an experimental result, there is not only one experiment, there are several experiments to back up that law. This is one such experiment performed by Faraday, where he has taken a coil of wire wound on a core on one side of the core, and there is another piece of wire connected on the other side of the same core. On the same core, he connected this section of the wire, this coil of the wire, to a battery. Okay, to a battery which should be having, you can say, sinusoidal current. Okay, because what I need is a time varying magnetic field. Okay, I need a time varying magnetic field. I don't need a static magnetic field, right? So the current was supplied to this wire, and the current was itself changing with respect to time. So it produces the magnetic field. Which is again changing with respect to time. But here, this circuit is not connected to anywhere. It is just connected to a galvanometer. But what Faraday observed, that there is a deflection in this galvanometer. This deflection in the galvanometer shows a small current in this loop of wire. What is the source here? There is no source here. Why this magnetic field? Why then this magnetic field? So you have this original coil of wire which is connected to the source. This is supplied with some current I. This produces magnetic field, and if the magnetic field is varied with respect to time, or if you keep changing this current, you will have the changing magnetic field, and that changing magnetic field produces electricity in this wire. Okay, and that is why you see a deflection in the galvanometer. In very brief and very, just few seconds, I have briefed this particular experiment, not spending much time here. Okay, and this simply was known as the Faraday's law of electromagnetic induction. A time varying magnetic field will produce electromotive force, EMF, and that causes electricity in a closed circuit which is nearby to it, the original circuit. The induced EMF, then it was calculated by Faraday, and the induced EMF was given by negative of the rate of change of flux minus d xi by dt. Right? If n is the number of turns, xi is the flux per one turn. If suppose the number of turns is n, then we call lambda as n xi, the total flux. Xi is the flux per turn. Okay, lambda as the total flux. These are some simple terms you must remember. Okay, flux per one turn, and lambda is the total flux, and the VEMF is then written as minus d lambda by dt simply, and that is equal to minus n del xi by del t. Okay, so this is again next formula where you can expect the question. The induced EMF in a circuit is minus n d xi by dt, where xi is the flux, n is the number of turns of the circuit. N is the number of turns of circuit, right? Either the flux will be given to you, or the magnetic field that is producing that magnetic flux, some information about the magnetic field will be given to you. This is the next area where you can expect the question, that is the Faraday's law. Okay, right? The Lenz's law, which is, you know, a sub part of the Faraday law, which is used to emphasize that why that minus sign is coming, that negative sign is coming, and that simply states that the induced magnetic field. Okay, now there was a current in this wire connected to the source. That current was varying in nature. That should be changing with time, so that we get a changing magnetic field. But that changing magnetic field, a time varying magnetic field, produced the current here. That is known as the induced current. Now this induced current, every current will produce its magnetic field. So this induced current will produce another magnetic field, but the induced current will produce a field in the direction that is opposite to the original field, opposite to the field that produced the induced current. That is what is simply the Lenz's law. Okay, the direction of the current flow in the circuit is such that the induced field, the induced magnetic field produced by the induced current is going to oppose the original magnetic field, right? Now V is equal to minus d xi by dt, and V is also equal to integral E dot dl. Comparing this, we can clearly say that, looking into this equation, we can clearly say that electric and magnetic fields are both related to each other. Okay, in the time varying situation, electric field and magnetic field are clearly related to each other. They are both present and they are both related to each other. What is the relation between them? I'll just write down here. What is the relation between them? Now see, what I can do here is, this is integral E dot dl. इसको यहीं पे continue करते हैं. I think that slide is missing. Let us continue this here, right? Line integral of electric field along a closed path, apply the Stokes theorem. So that will become integral del cross E dot ds. This is equal to, now this is minus d by dt of b dot ds. Integration is with respect to a surface, okay, not with respect to time. So the d by dt, it can be inside or outside. Okay, let's take it inside. So this becomes minus del b by del t. Let's take the partial rate of change, because b is also a function of space, but I only want the rate of change with time. So let me specify this clearly as the partial differentiation. Okay, now both the sides are surface integral. Compare both the sides, what do you get? Both the sides are surface to surface integral. Comparing both, you get del cross E is equal to minus del b by del t. So del cross E is equal to minus del b by del t. Del cross E, which was equal to 0 till now, for the static field it was equal to 0. That was one of the Maxwell's equation also, del cross E equal to 0. But for the time varying magnetic field, for time varying fields, dear, del cross E, for the time varying fields, del cross E does not equal to 0. The electric field is not conservative, but the del cross E is related to the magnetic field as minus del b by del t. This is your final Maxwell's equation, in accordance with the Faraday law. Okay, in accordance with the Faraday law. We will once again conclude the Maxwell's equation, don't worry. Okay, a review of the continuity equation, again to come back to the Ampere's law. The main intent is not the continuity equation, but again coming to the Ampere's law we studied. Continuity equation is actually given by del dot J is equal to minus del rho V by del T. J is the current density, rho V is the volume density. Okay, if del dot J is minus del by del T of rho V, let's have a quick recap of the Ampere's law. Ampere's law ने बोला था del cross H should be equal to J, right? So if I apply the divergence on both the sides, del dot del cross H, now divergence of curl is always 0. In a scalar triple product, whenever two vectors are same, the scalar triple product is always 0. Okay. So del dot del cross H is always 0. So del dot J should also be 0. Del dot J should also be 0. But according to the continuity equation, del dot J is minus del rho V by del T. Okay. So del dot J is minus del rho V by del T. That should not be equal to 0 for time varying fields. If there is a time varying situation, right? Suppose if it was 0, suppose equal kar dete. If del rho v by del t is equal to 0, what does this signify? That rho v is constant with respect to time, because only the differentiation of constant will be 0. So rho v should be constant with respect to time. That means rho v is not dependent on time. In that case, I can say rho v is not dependent on time. So if you have a time varying field, if you have time varying situation, if rho v is a function of time, then its derivative is not equal to 0. So for time varying condition, Ampere's law is inconsistent, incompatible. Ampere's law was found to be incompatible for time varying situation, and that is why a correction term was added to it. A correction term was added to it, and that was named as the displacement current density. Okay, the del cross H is J plus JD, and after again solving, we eventually know that del dot del cross H, this is the very basic vector identity, this is always 0. So del dot J plus del dot JD is 0. So del dot JD is equal to minus of del dot J. Continuity equation ko place kiya. So we get, del dot J is minus del rho V by del T. Now we know the relation Gauss law is applied. What is rho V? Del dot D. Okay, and after applying all these things, we get JD is equal to del D by del T. Rate of change of displacement flux. This is known as the displacement current density. A typical example of this is a current flowing through capacitor. This is a displacement current density. Now this is itself a very interesting and an important topic. Okay, although if I discuss this displacement current density in detail, it could take another, maybe 20-30 minutes. But let's right now stick to the formula. So displacement current density is the rate of change of electric flux density, or rate of change of the displacement flux density. D is the displacement flux density. The displacement current can then be calculated by surface integration of that. Okay. So we have the final Maxwell's equation, the final Ampere circuital law, which is known as the modified Ampere circuital law, and this is your final Maxwell's equation, next Maxwell's equation for time varying field. Time varying field, J plus dd. Del cross H is J plus JD. Yeah, let me be more specific. It is JC plus JD, where already we have told you J or JC is known as the conduction current density. Okay, what is the formula for conduction current density? That is sigma E. What is the formula for displacement current density? That is del D by del T. Or del D by del T can also be written as epsilon del E by del T, because D is equal to epsilon E, and epsilon is constant, so outside the differentiation, right? And with this, we can have the final form of the Maxwell's equation. Two of them are modified under the time varying situation. Let me hide myself. Okay. This is these two are the modified Maxwell's equation under the time varying situation. Although the Maxwell's equation related to the Gauss law and the magnetic monopole concept, they remain to be same without any modification. They remain to be the similar. Correct. This is what is the very final view of the Maxwell's equation for the time varying situations as well. For the time varying situation, have a look, everything is in front of you. Alright guys, okay, del cross C is minus del B by del T due to Faraday's law. Del cross H is J plus JD, and this is what we know is the JD term, displacement current density. Okay. Del dot D is equal to rho V, same Gauss law. Del dot V is equal to 0 because of absence of magnetic monopoles, and their integral forms are also mentioned in front of you. Right. So guys, in this session till now, okay, the EMT, we have covered up important formula of the electrostatics, important formula of magnetostatics, some important formula of time varying fields, and the final Maxwell's equation. This can be a very good, I'll share you the PDF in the Telegram group. The PDF will be password protected, and let's say the password is going to be TVF. I'll set the password as TVF, time varying fields. Just now we discussed TVF, so I'm going to place it as TVF. Okay. Okay, the password for today's PDF is going to be TVF. Where is going to be the PDF? I'll share you the link of the Telegram also. Guys, next session I will take on Monday. Okay, these are all major formulas summarized. Okay, at least, all important, more than 90% formulas summarized. Next, we will see you on Monday at the same time of 6 PM with the EMT, you can say part number 2, EMT part number 2, that is exclusively for EC. that is exclusively for EC. The topics that are exclusively for EV, the formula related to wave propagation, transmission line, antenna, waveguides, all those things will be covered in the EMT part number 2. That is scheduled for Monday at 6 p.m. Right? That is scheduled for Monday 6 p.m. Right? Yeah, we'll plan a formula session for mathematics also after some time. Yeah, Telegram link. So those who are wondering for the Telegram link, allow me just some time. I'll share you the Telegram link as well. Just a moment. Just wait a moment. I'll share you the Telegram link as well. Yes, this is the link of the Telegram. You can join using the link I've just mentioned. Mentioned here, right? Okay, and just to remind you, Sunday 9 p.m. we have the general session. As I mentioned in the beginning also, Sunday 9 p.m. we have the general session where we are going to discuss where I'm going to tell you what are the 3 common mistakes committed by aspirants in the last 3 months. Now November, December, January, 3 months are left. You should avoid those mistakes. What are the 3 mistakes that you should be avoiding in the last 3 months of preparation? I will discuss in a small session on the Sunday at 9 p.m. on the same BYJU'S Exam Prep YouTube English channel, the same channel where you're watching the session. So do not forget to subscribe to the channel in case you're not subscribed, so that you attend all such sessions, technical sessions, formula sessions, maths aptitude sessions, generic sessions, everything. Okay, chalo guys, bye bye. Okay, thank you, stay safe, take care, and see you in another session.